To make a mission-critical system fault-tolerant, you have to eliminate the single point of failure. You copy the data across multiple physical machines, so if one server dies, another takes over. But introducing redundancy breaks the core assumption of single machine programming, the illusion of a single unified memory. From a client's perspective, the base unit of state is a single shared register. Let's call it register X. When an application issues a read or write signal, it expects to act against that single definitive location. Spreading register X across a distributed architecture means every operation now has to update multiple isolated copies. Guaranteeing those updates happen atomically across every node at the exact same time requires a continuous, system-wide consensus. Because data is constrained by the speed of light and network latency, instant global synchronization is physically impossible. Nodes will inevitably fall out of sync. Without strict rules, concurrent read and write operations will overlap, collide, and return contradictory results to the user. To solve this, engineers implement a consistency model. This is a rigorous mathematical contract between the database and the client. It dictates exactly how and in what order those concurrent operations become visible across the network. This diagram illustrates the hard mathematical limits of distributed networks, defined by the CAP theorem. If the network drops packets or severs the connection between nodes, a partition, the system forces you to make a choice. You cannot guarantee both availability and strict consistency. It is crucial to distinguish a network partition from a node crash. Node 1 is not dead. It is fully operational, isolated from the rest of the cluster, and actively serving write requests. To remain available, it must serve divergent, inconsistent data. Note that consistency in this context is different from the traditional database definition. ACID consistency ensures a transaction preserves referential invariance. CAP consistency specifically demands that single operations are atomic and sequential across the cluster. These trade-offs exist even when the network is perfectly healthy. The pay-select conjecture extends the CAP theorem to state that during normal operation, engineers must still make a forced choice between latency and consistency. Modern web infrastructure requires continuous availability and microsecond response times. To achieve those metrics, system architects intentionally abandon strict absolute consistency in favor of tunable, relaxed models designed to survive network realities. This graph maps out an abstract database operation in physical time. It is bounded by two events, invocation and completion. If the bounding boxes of two independent processes overlap, those operations are concurrent. There is no absolute real-world order to them yet. Linearizability is the strongest possible single-object consistency model. It resolves overlapping events by forcing them into a total, globally agreed-upon order. Under this model, an operation doesn't take effect gradually. There is a precise, instantaneous threshold between invocation and completion called the linearization point. This is the exact microsecond the data mutation becomes visible to the entire cluster. The absolute rule of linearizability is visibility. Any read occurring before that vertical line will return the old value. Any read executing after it must return the new value. The system never serves a stale read once the linearization point is crossed. Guaranteeing that precise threshold is incredibly expensive. It requires pausing operations, routing cross-node consensus traffic, and forcing CPU cache invalidations across the cluster. Linearizability provides the perfect illusion that your database is running on a single machine. But by forcing operations to obey strict wall clock time boundaries, it imposes massive latency penalties that prevent large-scale databases from scaling effectively. To improve database throughput, architects relax the model. By removing the strict requirement of real-time global boundaries, we achieve sequential consistency. This diagram tracks two reading processes. Operations under sequential consistency are allowed to propagate through the network at different speeds. The primary rule is simply agreement. Every client process must observe the operations in the exact same global sequence, regardless of which event actually happened first in physical time.
The secondary rule protects the application's internal logic. A single process's own writes are strictly preserved in the order they were executed, its program order. Independent writes from other processes can interleave, but they cannot scramble the sequence originating from a single source. There is a mathematical limitation here. Sequential consistency is not composable. You can have two independently verifiable, sequentially consistent systems, but linking them together does not guarantee the combined result will be sequentially consistent. By dropping real-time synchronization, sequential consistency eliminates the heaviest consensus latency, while still protecting applications from reading contradictory, divergent histories. Imposing any global order, even sequential, requires overhead. If operations in a database never actually interact with one another, establishing a strict sequence between them serves no functional purpose. This timeline tracks causal consistency. It dictates that only operations with a strict cause and effect dependency must be observed in the same globally. Process 2 reads the output of Process 1 to calculate its next write. That logical dependency is locked in. However, concurrent writes with zero causal relationship are untethered. They can legally be observed in completely different sequences by different nodes across the cluster. Databases enforce this partial order logically rather than physically. They attach metadata called vector clocks to every message, tracking operation dependencies instead of physical timestamps, allowing the receiving node to reconstruct the required chain of events. Causal consistency provides the absolute minimum synchronization necessary to guarantee session behaviors, like reading your own writes, ensuring clients never observe a history that breaks logical causality. In highly distributed environments, databases like Cassandra and Dynamo abandon absolute ordering entirely to maximize availability. They allow replicas to temporarily diverge, resolving to an eventually consistent state. To manage this divergence safely, engineers implement tunable consistency. This architecture allows developers to dictate reliability limits at the exact moment of a query using three variables: the total replication factor, the write consistency threshold, and the read consistency threshold. By configuring the read and write thresholds to add up to a number greater than the total node count, you create a quorum. The system mathematically guarantees that any read operation will physically overlap with at least one node that captured the most recent write. To optimize the heavy storage costs of these architectures, systems utilize witness replicas. These specific nodes participate in the quorum mathematics to acknowledge writes, but they only record a lightweight log of the event, completely avoiding the storage penalty of copying the full data record. Tunable quorums give architects granular control over their network constraints. They can bypass static cap limitations, dynamically shifting the synchronization cost between read speed, write speed, and fault tolerance, depending on the exact needs of the application. This introduces one final architectural problem. If a system's availability model requires it to accept conflicting, divergent writes during a network partition, how does the database eventually reconstruct a single, valid state without deleting user data? The solution is strong eventual consistency, achieved through a specific mathematical structure known as conflict-free replicated data types, or CRDTs. This visualization tracks a commutative replicated data type. For this algorithm to function, the data operations must be both side effect-free and commutative. Isolated nodes can execute updates entirely locally during a partition, with zero synchronization. When the network connection heals, the system triggers an asynchronous merge. Because the operations are commutative, the order they were received in no longer matters. The merge function evaluates the vectors, resolves the discrepancies locally, and correctly collapses the isolated nodes into a unified global state. Designing shared memory across a distributed network requires accepting that absolute synchronization does not scale. Database consistency is an engineering equilibrium, balancing mathematical conflict resolution against the physical limits of network latency.